In lab number 4, we're going to build a single and a dual power supply. What's shown below is a bridge rectifier with a capacitive filter added onto it. Suppose that this input is a sine wave and has a maximum value of V sub Sm. Suppose further that this capacitor is not here. So when the input is positive and large enough, current will flow this way back through the diode, through the load back to the source. That's really this portion of this dotted curve over here. When the input goes negative, the current will try to flow back this way to the source V sub S. And that's really this curve inverted because the current through the load is always in the same direction. Now, if we were to put a capacitor across here such that the RC product is much, much greater than half a period, then when the voltage across the load is positive, voltage across the capacitor is also positive. Suppose that you're on this part of the cycle. You have a positive slope and the capacitor begins to charge. But when we get to the top here, the slope is actually 0 and then turns negative. The capacitor current then goes to 0, and then when it goes negative, it tries to come out of the capacitor. So it goes in the load. So what we're left with really is just an RC circuit that's discharging. At some point, the input will catch back up to the output, and then the capacitor can charge again. This is going to leave us with what's called a ripple voltage. It's a peak-to-peak value from the crest here, which is the input maximum minus the 2 diode drops, and then the low point is just that number minus the ripple. This RC circuit has an initial condition of V sub S maximum minus the 2 diode drops, and then is exponentially decaying with the time constant R sub L C sub L. And all this starts at some time t2, so we'll delay the start of it. It actually is only valid till the time t3 when the capacitor begins to charge back up again. The ripple voltage here is this peak minus this valley. So the peak is V sub S maximum minus 2 diode drops, and then the minimum value here is the value of V out at, in this case, time t3. We can use this equation here to evaluate that at the time t3. Got a common factor, we could pull this out. This describes the exponential decay in this interval, and it gets repeated over and over again. Now the interval t3 minus t2 is this interval right in here. The half period from here to here is t4 minus t2. That's almost the same size. If we do that, we can make a nice simple approximation and get a formula to get a handle on the ripple. If I were to approximate t4 minus t2 as t3 minus t2, again assuming that this interval is small, then I can replace the term here, t3 minus t2, with t over 2. Now, the sketch we had on the previous page, there appeared almost to be a straight line in this exponential decay, and it really comes from this idea that you can think of the exponential as a power series. And if the power is small, then squaring it and cubing it won't have much of an effect. In our case here, the value of x is a small number because we've picked R sub L C sub L to be much bigger than half the period. So we could then just substitute in here just the first two terms of the power series, which is 1 plus x, but x here is a negative number, so I put that here. These two terms cancel, and we're left with an approximation for the ripple. In lab, we're measuring the output, and so we could do this in terms of actually the output and not the input, and that's just define this as V out maximum. It's a little simpler formula to remember this. It's just the maximum output voltage divided by 1 over the period, which is the frequency, times 2 and R sub L C sub L. The average value, the effective DC value that we have is really this maximum minus half the ripple. This represents our DC component of our DC power supply. This represents an AC component riding on top of our results. Now we're going to use a step-down transformer to step the voltage down from line voltage to something in the 15 to 20 volt range. We also have a center tap transformer, which allows us an interesting possibility for a dual supply. If you recall from 202, an ideal transformer, the ratio of this voltage to this voltage is the ratio of the number of turns on this side to the number of turns on the primary side. In lab, N is going to be around 9, so if we did have a 170 volt sine wave, we're really stepping it down to about 19 volts. And then with a center tap, we can actually cut that in half and be able to play with a plus and minus signal. Now the ripple that's here, we can make smaller by putting bigger capacitors in, but that gives us larger surges of current, as we talked about in ECE 302. So here's another idea, that's putting a regulator between the load that we currently have and the capacitor and bridge rectifier. Suppose we pick this resistor R sub S to maintain the same ripple that we had before. Now, as long as the Zener voltage is less than the minimum value, which would be the average value minus half the ripple, then we'll keep the Zener diode turned on in this direction. The average voltage here, we just calculated, it's a DC value, so that average voltage minus this average voltage, which is essentially constant for the Zener, not much variation, divided by the resistance would give me the current, or I can exchange those two and be able to pick the resistance by knowing the average voltage and average current of our previous configuration, which is really the value of R sub L. Suppose that Vout had an average value of 17.5 and we had a 3 volt peak-to-peak ripple. Now we're using a 12 volt Zener and a 1K load. These are around the values we're going to use in Lab 4. The Zener voltage, if Vout is 17.5 and the ripple is 3, needs to be less than 16. And so a 12 volt Zener should work pretty well. And then using this formula, we have the average voltage minus the average voltage of the Zener divided by the average current coming in, which would be the 17.5 divided by 1K. In the original design, we get 315 ohms. This will preserve the same ripple characteristics we had before adding the Zener. And we're going to see this in lab. We're actually going to measure this. If you think of this last design as having a load, having a Zener diode, a series resistance, and a capacitor. But now doubling everything, having two of the same components. Previously we had the ground over here. We had a output voltage that was fairly constant and then a ripple that's over here. If we double everything, put two Zeners, two capacitors, think of the load as being in two pieces, and really two series resistances, but now move the ground over here, we wind up getting, when the current flows through the Zener, like it was through the load, we're going to create a positive voltage here and a positive voltage here. But with respect to the new positioning of ground, this would be V sub Z and this would be minus V sub Z. We're going to make a 12 volt power supply single-ended, and then we're going to take and replace the 12 volt Zener by two 6 volt Zeners. We'll be able to make in this way a plus and minus 6 volt power supply. We're going to use this later in the lab to build a power amplifier, so we could actually power it with this power supply. We won't rebuild it, but the purpose of this was to show you that we could build one that could power that. The concepts covered in Lab 4 are transformer turns ratio relationships, full wave rectification with capacitive smoothing, ripple voltage estimation, Zener diode shunt regulators, and we're creating a complementary supply by redefining ground. As far as techniques go, we're going to use the Infinium toolbar to measure average voltages, peak voltages, and peak-to-peak voltages, as well as frequency. We're going to measure capacitance with a LCR meter. And lastly, we're going to use the Infinium math functions to differentiate a capacitor voltage to estimate the current that's flowing through it, which would be related to our diode current. And this is Lab 4, building a single and a dual power supply.